started. Dynamic analysis. So we did a nice foray into static analysis. We looked at a whole bunch of static stuff. And now let's look at dynamic stuff. The difference being what? What was the difference between static and dynamic?
Execution. Dynamic has only one particular execution.
Yeah,
That looks at the whole code.
So with static, we're considering all possible executions at once. Now with dynamic, we're just considering one single execution, one representative. So, yeah, sometimes we just want to look at a single behavior and might ask, did my program ever do something? How did X happen? Where am I spending my time inside a particular execution? Where might I parallelize an execution based on its observed behavior? How could I tolerate errors better? And how can I better manage memory and resources? These are things that you can answer dynamically. So let's just give you a small example here. This is obfuscation. You can take a program and restructure the code so it's almost impossible to interpret. This is called obfuscation. And this is something that you often see inside things like DRM or digital rights management. So the system that Apple uses, for instance, with iTunes is called Fairplay. They don't want people to understand how Fairplay works. Because if people understood how Fairplay worked, you could disable the restrictions on iTunes MP3s or whatever they use, right? And play them on other devices. Apple doesn't want that. However, you can use techniques that are dynamic in order to turn something that looks like this, that's difficult to interpret, into something that looks like this, that's easy to interpret. Transform something that's obfuscated into something that's understandable. Using dynamic techniques, by observing what actually happened. So how does this work? Well, one approach to dynamic analyses is to take the input in the program and produce a trace. You can record the execution. Then you take your analysis and run it over that trace and produce some results in the end. Okay? So we're recording a trace and then we're doing what's called post-mortem or offline analysis after you've got this recording. This, however, has some scalability issues because you need enough space to hold that trace. And for long-running executions, when you record the execution, that trace is going to be really, really large. It's recording a lot of data. So in contrast, you can also perform some analyses online, and some analyses you just want to perform online. Garbage collection is an example of a dynamic analysis. You probably want that to happen while the program is running. So how does this work? You instrument the program ahead of time, and then this modified program invokes this instrumentation to analyze itself or to manipulate itself as it's executing. So it's performing an online analysis. And garbage collection is an example of this. And you'll often use an abstract domain similar to what we saw in data flow analysis in order to simplify things and make them more efficient. So let's look at one possible example. Say we want to do basic block profiling. You want to know what code gets executed a lot. That's probably a common goal. How many of you have done something like this? 2. Okay, maybe less common goal than I thought. If your program is slow, you want to figure out where it's spending its time. Figure out what code gets executed frequently. One way of doing this is counting how frequently you execute the instructions.
Will if Intel compilers provide something like this? You
Yes,
just run,
absolutely.
you collect the...
Absolutely. Nowadays, you can have some hardware counters that are used to help with this as well. But absolutely, Intel and other compilers definitely have support for this, even without hardware support. So how can we modify our program to do that?
Put counter at every, at the beginning of every function.
Yeah.
Execute program. Check the statistics.
At the beginning of every function?
Like you can take an approach where you look at it for each function and then you go to that function and then put counter in all smaller functions. So that
This is true. So what you're describing is actually called profile-guided instrumentation, which I'm not going to mention until much later in the slides.
So or you could just put counter for every instruction.
Yeah. That's or maybe middle ground. Counter for every basic block. Like that's an easy way. We can zoom in on every basic block. At the beginning of every basic block, we find its ID, and we just increment a counter for that basic block. This is the easy way. There are much harder ways that are smarter than this. This is the easy way. And you have to remember that before the program starts, you want to insert something that sets all the counters to 0. And after the program finishes, you want to have something that prints out all of your counters or saves them to a file somewhere. So don't forget that you need these things as well. LLVM also has fine support for doing this stuff automatically too. And there's an example in the LLVM demo. Okay, so how efficient is this? If we have all of these counters, then we're performing all of these extra operations. We might be detracting from the efficiency of our tool. That's not desirable. Right? You could affect the actual performance by doing instrumentation. And if you're trying to measure the performance, and you're affecting the performance, then your results are going to be kind of, well, slightly ambiguous or invalidated. So you want to affect the performance as little as possible. Can we do better?
Several runs could be.
We could run it several times, but even just in terms of our instrumentation, do we have to perform all of these increments? You're shaking your head.
You can only count like the 0, 1, like 1 and 2 will be.
Okay, so you said we could count 0 and maybe count something like this, and we can figure the others out. Yeah, that's perfectly reasonable. So we can cross off some of these, and well, now count 0 is equal to count 3, right? And count 2 is the same as count 0 minus count 1. So we can be a little bit smarter. Can we do better?
So obviously count 0 will be executed more number of times than count 1.
Yes, this is true.
So we would just consider count 0 instead of 1.
But if we only consider count 0, then we don't know how many times these different branches were taken. So we need some information for the branches. But count 0 is the same as count 1 plus count 2.
Yeah.
So we'd actually be better off by going in as deep into the structure as possible and instrumenting those branches instead, instrumenting those basic blocks. Because if we have an execution that takes this path, for instance, we'll always be performing 2 increments. And we'll always be performing 1 increment along this path if we have this instrumentation. But if we just instrument these 2 basic blocks, we'll only perform 1 increment along this path, and we'll only perform 1 increment along this path. Right? So you can take these sorts of issues into bearing when you're doing instrumentation, when you want to figure out how to do instrumentation efficiently. Okay. So what are some of the tactics that you use? Well, you can use abstraction to make things efficient, where you'll take a bunch of states and represent them as a single state, again. You can identify and avoid redundant information like we did on the last slide. We're no longer double counting anything. You can use sampling. So sampling might be where, okay, we want to perform that instrumentation, but maybe we'll have 2 versions of a function. One where we do all the counting and one where we don't. And maybe 50% of the time, we'll call the uninstrumented version. That's sampling. The results aren't as accurate anymore, but we don't affect the performance. And you also have compression and encoding. We mentioned this when we started talking about slicing and traces. Doing slicing and tracing effectively is very much dependent upon compression and encoding nowadays. Making sure that your traces are as small as possible. And we also have things like profile-guided instrumentation, where you can do one pre-pass, you can execute the program once to figure out what's interesting, and then only instrument those interesting things a second time, and refine your process. Okay. So let's consider a particular problem, path profiling. We looked at basic block profiling. Let's consider path profiling now. How often does an acyclic path execute? How many times? And I should mention this topic is related to the paper for next Tuesday, if someone wants to volunteer. So we could log the trace, right? We could go through and every time we get a new basic block, we could record that basic block to some trace, to a file somewhere. And maybe we've got buffering, that's okay. We can ignore buffering for now. Let's assume everything is well buffered. So we could log everything and then record the path at the end, right? Or we could encode the paths. So we can be a little bit smarter and say, well, maybe every path has one ID, and instead of calling some expensive logging function at every basic block, we can just add some extra instrumentation, some arithmetic operations along the path, so that we compute the ID along the way. So we can be a little bit clever about the structure of the graph to make this happen. This is an example of encoding. Okay? And we're going to walk through how to do this. I see you missed about. Okay. Okay. And you can see here at the end, we can maintain a count of every path and just increment the count by 1, and then just dump these counts to a file at the end. Much cheaper than recording everything to a log. So step 1 for doing this would be to count the number of paths from each node to the exit. How can we do this? Well, we can start at the exit and compute the number of paths to itself. There's one path from the exit to itself, because it's the exit, right? And then we look at its ancestors. And we say, well, there's one path from E to F. And there's one path from, well, no, there are two paths from E to F, right? Because we can either go here, or we can go here. And so that there are two. Okay, reasonable enough, right? Now we have two paths from C to F, because this is there's only one path from C to D, and so we can just inherit it, right? So you can see that these values are flowing backward. They're flowing backward along the control flow graph. It's a dynamic programming problem. Yeah, we have 4 here because there are 2 here and there are 2 here, and we just add them together, right? So you can look at the successors and add them together. So that's why we got 1 for this. There's only one successor. 1 plus nothing is still 1, so we just get 1, right? So the sum of your successors, of the paths for your successors, is your own number of paths to the exit.
A should have 6.
A should have 6, exactly. Right. So we're flowing these values backward through the program, doing dynamic programming. And then what we do is partition the encoding space locally at each node based on these numbers. That sounds complex. It's not as complex as it sounds, right? Because there are 4 paths from B to F, we know that any path that starts with AB can fit within the space, the number of IDs, starting at 0 and less than 4, right? Because we've counted the number of paths, there are only 4. So we can give those paths the IDs 0, 1, 2, 3, right? So we're partitioning the encoding space. That's what we mean by it. We're just giving the paths that start with AB a certain range. And anything that starts AC then has to be 4 or 5, right? Anything that starts with AC can't have an ID in the range of 0 less than 4, because those are reserved for AB. So AC has to start after that, at 4. So you can see over here the process is that you add the number of paths to the previous successor in order to find what you're going to add as an increment along the path to partition the space for the next one. So when we look at C, any path starting with AC is going to be in the range of 4 and higher, right? So we add 4, because that's what we considered as the number of paths to this node, from this node. And if there were another one over here, if we had ABG, right? Then what would we add along this path?
4 plus 2, right?
4 plus 2, right? Because the encoding space for anything that starts with AG has to be after all of these, which are in the range of 0 less than 4, have to be after the range for these, which are in the range of 4 and less than 6. So they have to start at 6. Okay? I sense confusion? Maybe not? Okay. Okay. We'll keep walking through it. If this confusion is resolved, excellent. Okay, so along this edge we add 4, because that's how we need to partition the encoding space here. When we come down to B, well, we look here. There are 2 paths along this, this route, ABD, and there are 2 paths, ABC, right? So because there are 2 different paths going from D, we look at this value here, we have to add 2 along this edge. So the paths that go this way are in the range 0 less than 2. And the paths that are along this way are
2, 3.
2 and 3, right. They're in the range of 2 and less than 4. So we're just dividing the space up further as we progress along. And then we're adding the appropriate things based on the number that we've seen and the sum of the other successors in order to compute exactly what that partitioning is. Okay, so then when we come to D, well, there's one path this way, so in order to differentiate these 2 routes, we have to add 1 to this edge. So that way this has 0 and this has 1. And even though this can be executed with different prefixes up here, well, let's see what happens. If we take A, B, D, E, F, we get 0, right? If we take A, B, D, F, then we get 1. So the distinction here works. We refined things that way. If we take A, B, C, D, E, F, what do we get?
A, B, C.
A, B, C, D, E, F.
2.
2, right? So the distinction here doesn't, well, let's do one more. Let's do one more. That'll make it clearer, I hope. We could then do A, B, C, D, F, and we get 3, right? So you can see all the possible 4 paths that take the route A, B, and how they're split up. And you'll see that this does this coarse-grained partitioning with the value 2, and then we subdivide the suffix of the paths, whether you take DEF or DF, with this at the end, by adding 1 or not. Okay. I'm seeing some nodding.
Can you go over this once again?
Okay.
From that, when you divide it into 4 and 2, starting from 8.
Okay, sure. So there are 4 paths from B, right?
Okay, yeah.
So that means that we can encode those 4 paths with the first part of the encoding space, 0, 1, 2, 3, right? And that means these must be
4 and 5.
right, exactly. So then the question is, how do we subdivide those? Well, let's look at the 4 and 5. The 4 and 5 then comes down here and can take 2 different paths. If they go this way, what is it? 4. It's 4 because we don't add anything. If they go this way, then we further subdivide the encoding space using this, and we get 5, right? Clearer? Okay. So we can also optimize things a little bit. You know, we have this ID equals 4, ID equals 2, or ID plus equals 2. If we know that this is the first time we're going to be setting a value other than 0, we can just make that a definition and not increments or an addition. And so that avoids some extra work, a moderate amount of extra work. But if you're worried about performance, maybe that's relevant. So how are we going to decode this? Now we have these IDs, and we know that path 7 executed, well, we don't have path 7, and path 3 executed 50 times, right? What executed 50 times? We probably want to be able to move backward from this ID, this encoding, to the actual path. So one way is to keep a dictionary, right? So we look at all the possible paths, we define them, and we say this is the ID for that path. But we saw that we could have combinatorial explosion. You know, the number of branches you see increases the number of paths by 2 every time. So if you have even a small number of branches, this might not even fit in memory.
So you would only take and put those paths in the memory which are executed and increase the count for that. Say if one path is executed, I'll put that path name and the count.
Okay.
If another path is executed, I'll take the path name and count.
Well,
Others I will not even put in memory.
It sounds to me then like you're back to logging then as well, because you're also recording the path in order to do that. In order to figure out
So
both
my
the ID
path
and
is
path.
the ID, right?
Ah, but you don't know what path that ID represents. You just know it's an ID. You know it's a number, but which path through the graph is that? You
But
know?
if you have a structured way of doing it, we would know exactly. For example, if I just say that first bit is 0 for this. one
Okay,
and one
okay,
for this.
okay, exactly. That's not a dictionary though.
Okay.
That's a smarter way.
Okay.
In fact, maybe that's the way we'll be using it. Instead of using this dictionary where we store each path and its value, we're going to decode things. So we can just follow the control flow graph and only one path will fit that ID. So we start off, for instance, with ID 3. Well, ID 3 is less than 4, right? So which way did we go?
AB.
AB, right? Because it's less than the number of paths there. So we had to take that path. Now, we've still got 3, so which way did we go?
Either BC or BD, right? We don't know.
We do know. We do know. We take, which way?
No, it will be BC or VC.
ID
No,
equals-
it says that it has to do.
Okay,
BC
right.
will set to 2, and then you do +1, and you.
Aha, right. So the question is,
But the
where
thing-
are you in relation to the count? Well, 3 is greater than 2, right? So it can't be this path. So we must have taken this path. If we're greater than the thing that comes next, or equal to it, then we must have taken this path.
So it's not like knapsack problem where you try to.
No. It can be precisely encoded. It can be very precisely encoded, and it's not NP complete.
Oh, okay.
It's very nice as far as problems go. So we must have taken -2. Oh! This is the operation. When you go along this path, remember this path adds 2 essentially, or sets 2 to the value. So you have to subtract 2 when you go along this path during decoding.
So ID should always be less than the number in the yellow circle, kind of, at this
Yes,
step?
yes, absolutely. Because this is the number of paths from this node. And so the encoding space from that node should fit.
Okay.
So we have ID 1 here, right? And that means, well, we only have one option from C, right? So we must have taken that. But we have ID 1 here. Which path did we take?
DF.
DF, right. Because this would have been a 0. So now we've gotten 0 at the end. We've precisely decoded it. So we've got encoding and decoding. And it's efficient. And it's easy to compute just by doing some arithmetic on these paths. Nice. Okay. So these are the actual overhead results that they presented. How would you interpret these? We have a base time. We have what they measure as path profiling overhead. They have some extra optimizations, but they're basically just what we presented. Any ideas? Is this good? Is this bad?
1 second.
What is the Q?
Just some optimizations. We can ignore that. You can pretend it doesn't exist. We can see that they have these results, and then they present averages down at the bottom. Are these results good?
44% of something. It's good.
44% overhead. Well, 44% overhead.
Ah,
So they're
overhead.
adding 44%.
It's okay. Well,
They're
more than
adding
like you have
44%
30.
instructions to the
They're adding
existing-
44% to the runtime.
Okay.
No, it's okay. I mean, you have just 1/3 longer.
It could be. It could be. Is 44% acceptable? Maybe. When you're profiling, if you ever add profiling instrumentation and run, which apparently not all of you have done, or most of you haven't done, if you tried profiling code to see where it spends its time, it's probably gonna, with just standard profiling that exists in most systems, it's not gonna be that, or maybe a little bit longer. You'll probably see more overhead than that.
No, look, for GCC, right? They have overhead, for example, 96%, which means compilation or something takes.
This means that running GCC on sample benchmarks. So what they're doing is they're running GCC on some standard benchmark inputs. They're running Perl on some standard inputs.
So overhead is 96. It's twice as long. It's
Twice as long.
terrible.
Well, depending on the scenario, but you recognize something. You recognize something. What did you recognize? I pointed out these averages, and we saw 44. And then you said, well, no, there's a specific one up there that's 96.
Okay.
Averages are misleading. You have to be a little bit careful about this. Especially when you're interpreting results, there's a strong tendency for people to say, you know what, we get this nice average performance, and that's meaningless. Because you have to look at these subcases and start to understand them. In fact, for overhead results, frequently, an arithmetic mean for averages isn't even appropriate.
Maybe a geometric mean.
A geometric mean is
Or
more
when
appropriate.
it is x times something.
Yeah, yeah. So if you see this normalization where you're seeing something like percentage overhead, you probably want to use a geometric mean. Okay, and especially if you see a whole bunch of different benchmarks in here, every one of these benchmarks means something different, right? So the results aren't necessarily comparable. A geometric mean is less biased by an individual benchmark.
Yeah, if you will remove GCC, your overhead would be even lower. You can say, "Wow, it's such a good results."
But
Sure,
GCC
sure. But maybe that's actually good. Maybe in terms of a summary, really an average, some notion of an average, whether it's a geometric mean or an arithmetic mean, is a notion of a summary. You're summarizing results. In practice, you probably don't just want to present a summary, you also want something like the distribution of the results. If you present the distribution, it's an even clearer picture. That's best practice today, to present a geometric mean and an actual, say, standard deviation or distribution of the results. Otherwise, things can be misleading. And even then, what they should do in their results is drill down into the details and say, well, you know, they were this good in summary, but we have this corner case, and here's why. Okay. So, when we look at how dynamic analysis fits into these notions of approximation, we saw the same slide when we introduced static analysis, right? We have this over-approximate behavior, we have under-approximate behavior, and one execution is a type of under-approximate behavior. If you have two different under-approximations, they may or may not overlap. But it's a subset of possible program behaviors. So we've got, with dynamic analysis, the actual analyzed results are a subset of the feasible results. And as the number of tests or execution increases, as you perform more executions, you can fill this space out more to the set of possible program behaviors, right?
if you are intelligent with the inputs.
If you're careful about the inputs, absolutely. And we'll start to actually, there's one of the papers we're going to look at which talks about how to use tests to prove things about program behavior. And it's going to look at exactly that sort of issue. How do you choose those inputs intelligently? With static analysis, the set of feasible behaviors is a subset of the analyzed behaviors, which is why you could have something like this, where it's not really possible to have an error, but we report that there is one. And as the number of infeasible paths goes down, the analyzed results start to reflect the feasible. These two areas complement each other. One, as you have more executions, you start to fill out and grow from inside the possible set of behaviors to meet the actual set of program behaviors. From the other, you're on the outside, and if you can reason about things not being possible, like these, only taking one of these branches, true branches, then you can start to make them both move towards the actual program behaviors. Increasingly, analyses combine static and dynamic approaches in order to do that. in order to be more precise, in order to be more usable. Okay, so how and when do you want to actually instrument your code when you're doing dynamic analysis? Well, you can do source or IR level instrumentation. This is what tools like LLVM, SIL or SUT do, or WALA. LLVM you've seen, hopefully. SIL is something that lets you analyze C program source code, and SUT lets you analyze Java and JavaScript, and WALA also lets you analyze Java and JavaScript. Any of them would be perfectly fine to use in a final project. So you essentially compile the code in a way that doesn't really compile it, just looks at the source, analyzes it, and maybe spits out some new source code. Or in the case of LLVM, actually does compile it. It does require a dedicated analysis and build pass. If I want to do dynamic analysis with LLVM, I need to compile a new binary. Okay? I can't perform tracing without creating a new binary with tracing instructions and then running that new binary. So if I already got something compiled, can't analyze it. This is a big limitation. With static binary rewriting, you can take a compiled binary and insert instructions into it, but this is, again, technically an impossible problem to do safely in general, so there are some risks involved. With dynamic binary instrumentation, you run a program, and as the program runs, it is interpreted, just like a JIT inside the JVM. And so when you encounter a new binary basic block, the program will say, okay, here's the set of instructions in that basic block. I'm going to analyze that, recompile just that basic block, generate new code for it, and execute that new basic block. So you're dynamically inserting code, but you're still always instrumenting before you execute. The nice thing here is that you can adapt your behaviors at runtime. You can change what the analysis is doing at runtime, and you can always use the original binaries. But you have less semantic information about the structure of the program, because you throw that away when you go down to a binary representation. Because again, you don't even know necessarily what is code and what is data once you've compiled down to a binary. So in general, you start off by doing instrumentation. And this is even true in that last case we saw before. Even though you instrument as you execute, you start off by instrumenting code. Then you execute this instrumented code in order to analyze the behavior, and then you'll do some post-mortem analysis over logs or whatever. It's very, very common for people who start off doing dynamic binary instrumentation to mix these two stages. They think that the instrumentation phase is the execution phase. If you choose to use a tool like Valgrind for your projects, then chances are you'll make this mistake. Almost everybody does it the first time. So just look out for it. Okay, 5 minutes. We won't quite finish with this, but we'll mostly finish with it. So if you're doing static instrumentation, you compile the whole program to IR, you instrument it, you generate a new program that performs your tracing or analysis, and you execute it. Big picture, I'm beating a dead horse at this point, but hopefully that's because well, no. It is because I want you to remember it. Hopefully that's actually what happens. With dynamic binary instrumentation, you compile the program as usual, you run it under an analysis framework, and then you instrument the program as it executes. But you still instrument the program before it executes the instrumented code. How many of you are familiar with von Neumann machines? Or just the fetch execute cycle? Okay. Also very few of you. But in general, it's just the idea that the machine is going to go out, find an instruction, and execute it, right? Oh, you finished with one instruction? Well, what was the next instruction? The processor is going to go out, find the next instruction, pull it back, and execute it, right? Really, this is just a modification to that. What is the next instruction? Oh, go and fetch it. If it needs to be changed, change it into new instrumented code. Now execute it. Oh, what's the next instruction? Find the next instruction. Pull it back, change it into new instrumented code, and execute it, and so on. So it's just a slight tweak to that standard operating procedure. And instead of operating on an instruction at a time, usually it'll still operate on a basic block at a time. So you instrument a basic block at once. And one example of this is the tool Valgrind. How many of you have used Valgrind? Okay, one of you who may have used it in a previous course related to this. Anybody else?
I've used
One
pink.
You've used PIN. Okay, that's something. PIN and Valgrind are very, very similar. I would say they're analogous. PIN, perfectly good alternative. These are binary analysis infrastructures. If you're not using tools like Valgrind to look for, say, memory leaks or what have you, it's a very good tool to use. It helps you find memory errors. Address Sanitizer is another one of these. Instead of using dynamic binary instrumentation, it uses static instrumentation. It comes with Clang. It is built into Clang. So if you want to do some extra memory safety analysis, you can just compile with a few extra options, and Address Sanitizer will just work for you. It uses static instrumentation, so it instruments when you compile and generates a modified binary. And it will find use after free bugs, where you use some memory after it's been freed, and you can find buffer overflows for heap, stack, or global memory. And it'll automatically find them and report them for you. So that's rather nice. These are pathological bugs in general. And this is used extensively at Google. In fact, every release of Chrome is tested extensively with this enabled. Every release of most Google software now is tested with this enabled. So how does it do that? Well, I guess we'll get through maybe 2 or 3 steps of this. First, it replaces malloc and free. So this allows it to recognize what memory gets allocated and what memory gets freed, right? By having their own implementation, they can recognize that. Then they look at all of the memory that's malloced. And if you allocate, say, 10 bytes, well, it'll allocate, maybe 50 bytes, but there's going to be a buffer before it and a buffer after it that it flags, that it poisons. What it calls this is a red zone. And it'll return you a buffer to an appropriate point in the middle. And freed memory is poisoned entirely. So if you've got this chunk of memory that you allocated, you'll poison the whole thing when you free it. And then the space around buffers on the stack are also poisoned. Oh, my tricks are showing. Okay, I should hide that. So if you've got some buffer on the stack, well, the address to element 0 is at the bottom here. The address past the end of the buffer, well, I guess this should actually be a little bit higher. Buffer 5 would have been past the end, really, is at the end of this space. So an access below or above the valid buffer range will be poisoned, right? So what they do is report any access to poisoned memory as an error. It's a very simple strategy, right? You just add in some extra memory and report accesses outside that as poisoned. The way it does this is by just putting a check in front of every memory access. And it turns out that's relatively efficient, relatively. And they actually recommend using this in some cases on deployed code, believe it or not. This is pretty simple. You just check is poisoned, and if so, then report an error. And that's it. So how do you determine if it's poisoned? Let's leave that till next time as part of the magic. There isn't much left. We're almost to the end of dynamic analysis. So next time, well, next Thursday, or this coming Thursday, I will present an example paper, right? Try to read everything except section 5. You can ignore that. It's the longer, maybe not as interesting in my opinion one, but, and then we'll finish up with this next Tuesday. We'll discuss testing a little bit next Tuesday, and we'll have enough time, because there's really nothing left here. We'll have enough time to discuss interprocedural or context-sensitive static analysis next Tuesday as well. And we'll actually have enough time to get through all of that in less than an hour. And someone else will present a paper. Someone who hasn't volunteered yet, but will volunteer, will present a paper next Tuesday. Okay. This is the advantage of volunteering before Thursday, is that you know if you're presenting next Tuesday or not.
Oh. Okay, because Tuesday is deadline for the project, so you have to do the project and read the paper. Oh, geez.
Yeah.
No, I'm not the volunteer, no.
So you could be volunteering.